don't worry, Jake. We already pinned Dave as the reason you lost.
Okay, so I want to spend a little time today. Last time we talked a little bit more about client-server alternatives. We talked a little bit about common ports. We started moving towards distributed networks, but I want to look at the actual file format for a few minutes of Bit-torrent, so we kind of understand how this guy actually works. Let's see, I'm going to make this a little bit bigger. So file structure. So it is a binary file, so you couldn't just open a thing with a text editor, but when you actually start reading it in through an application, you can read the various chunks of it. So let's see. So what's up?
Nothing. I was just reading that.
Oh, because I actually originally was going to write a quick reader of the thing and use a 50 Shades of Grey torrent as our example. So to read in from a binary file. So in any case, we have the URL of the tracker. So the tracker is the guy that that's that Mr. Torrent, Mr. Bit-torrent, that keeps track of all the dudes that are currently part of this. Info, this is the names of all the files. You know, when you, not that any of you would know this, but when you open up a torrent file, it shows you here's the 5 files associated with this guy. Yeah. That's stored in a data structure called a dictionary. Not important. Each one's going to tell you the name of the file and the length number of bytes in the file. All right, so that's going to give you the. Okay, so as an example, this would be the source of the announcement. Here's the name of completely legitimate Linux. This is Debian Linux ISO, so perfectly. We all download our Linux distributions via torrent. Here's the length of it in terms of the number of pieces. And these are the individual hashes of the pieces. So it looks like there are this many pieces, this length per piece, and these must be hashes of each of those individual pieces. So there would be 262,144 hashes, something like that. All right. Here would be an example if there's multiple files associated with it instead of a single file, same exact type situation. So somebody's going to host this, that is Mr. Torrent. So you go and you put down, you download this file from somewhere. When you open it up, it's going to have the tracker URL for where Mr. Torrent lives. And that's the guy who's going to keep track of all the other people that come in. So he hooks everybody up. He knows about the IP addresses of all the people that are on the current network. Kind of makes sense? What if we were writing this ourselves? How would you write Mr. Bit-torrent? What would he do? So if we had a slide here, Mr. Torrent. What does he do? So he accepts an incoming connection. What does he do with it? How does one start off? Let's say you have a file on your computer and you would like to share this file with the world. How do you start that? Well, we only steal files. Who shares a file? How would you go about doing that? You have to go let somebody know that you have to put this torrent somewhere to host it, so somebody can download it. Correct? Okay. So if you wanted to handle it all yourself, I mean, there's torrent hosts out there as well. But if you wanted to host it all yourself, what would you do? You would create a website at GoDaddy, let's say, and on that website you'd put your actual files, individual files, so the original, and then you'd also put the torrent address, or you put the torrent file for other people to download, because it's quicker for them, because we don't want to run into this client server problem where they have to download a gigantic file from one central source. Instead, we're going to give them a little tiny torrent file that, so you have one server hosting a 100 kilobyte file, which is quickly downloaded by people, right? So it's not going to bog down that host. And that 100 kilobyte file is being served in a client server fashion. Once you have that file, it gives you the instructions on what to do next. So in this case, we are sharing the file from the same source. Probably not what you want to do, but in our little world, it'll work out just fine. So we have our setup. So this is our web server. And on this server, we have our blah.torrent. And we also have the actual large file, which is blah.iso. Okay, so blah.iso, let's say that this is 5 gigabytes. Blah.torrent is 100 kilobytes. Okay, so those are the two files. So now this dude comes along and says they somehow stumble upon your website that has a download link for blah.torrent, and he downloads this file. So that's an individual connection to the server, doesn't take very long, and now he has in his possession the blah.torrent file, which has the instructions on how this works, right? Similarly, somebody else comes along, downloads blah.torrent. So now we have 3 different locations all with blah.torrent. Here's the original host of the data, and here's 2 guys that want the data. All right, now blah.torrent happens to tell them, oh, what you're going to do is you're going to connect back to, in this case, the exact same server, because that's where blah.iso lives. Okay, but Bit-torrent splits blah.iso up into pieces, small pieces. Okay, so on this guy's server, this guy is sitting there as a full file, but the Bit-torrent protocol streams this file in chunks. That makes sense? So if we're building this, when this guy opens up this blah.torrent file and it says, okay, connect back here, go ahead.
Would it be better, you said it splits up in pieces, would it be better to ask to download the last pieces first, because then you could request some of the first pieces from someone who is just starting? Actually, that wouldn't work either.
Well, what you're suggesting is there an optimal order in which to request the pieces to get the best performance?
Yeah.
Potentially, yes, but I think you'd still be guessing because you don't necessarily know what the rest of the network looks like. You might know how many seeds there are, how many people are seeding the files, so you could make some intelligent decisions about that. So if there are 500 seeds, maybe you choose to download, let's say there's 500 pieces. There'd be more than 500 pieces, but maybe you decide that you're going to split it up so you get all maybe the first 400 pieces from one place, the next 400 pieces from another place, the next 400 pieces from another place. At the end of the day, you're saving yourself maybe a little bit of time, or maybe you're costing yourself a little bit of time. It's kind of you're rolling the dice, because you don't know if when you went in there and you decided I'm going to download the first 400 parts from this one place, they might be a leecher, and in 2 seconds they're gone. Okay, now you've dedicated yourself there. So when you don't get the completion of this, now you have to go back out and fulfill those buckets. Because remember, we advertise this as being kind of like an array here by this example we were just looking at. It would be an array. What was the number in there? Yeah, here's the node, the nodes that are actually on the network. So there's 262,144 pieces that we're going to split the file up into. So we're basically going to create an array of 262,144 buckets, and each bucket is going to hold this many bits. Actually, no, other way around. This many buckets, each one containing this amount of data. So 256 kilobytes. So that you're going to be downloading 256 kilobytes per piece. So why do you think it's so small? Why are we grabbing 256 kilobytes instead of 50 megabytes? Because of the number of leechers, the amount of data you can get from one source might be limited, right? So you'd rather get 256, 256, 256, 256 4 times from the same source rather than try to get 1 megabyte once from that source, because they might drop off.
Would it also be possibly that they made it fairly small so that if there were a lot of seeders, not like it ever happens, but like if there were a lot of seeders, then you could take advantage of the fact that there's a large amount of them?
Potentially, but if you are using BitTorrent to download stuff locally to your machine, is it always better to be downloading the pieces from multiple sources? So let's say there's 500 pieces, just use that as an example, and there's 500 seeders. Is it always going to be best to download one piece from all 500 seeders instantaneously? Your gut says yes. That, oh, okay, well, if I have 500 people who all have the entire data, and I can get one of my 500 pieces from each one of those at the exact same time, and I'm getting 256 kilobyte chunks, I should be able to get the whole file almost instantly. Right? Is that good? We have kind of a small example here with 500. Let's say it was 5 million. So we have more sources. So 5 million, it's 500,000, that's 5 million, times 256 is that, divided by 4, is that's the number of megabytes, by about 1,024, that's the number of gigabytes. Oh, big enough file. Big file. Okay, so that'll be plenty for our example here. So we're going to download a 312, is that 312,000?
Yes.
Yeah, 305 terabyte file. So we're going to download a 305 terabyte file. And there's 5 million people serving the file, and they all have the entire contents of that file. Completely unrealistic, but let's just go with it for this example because it gets me where I needed to get me.
It's a research study on donuts over years.
Okay, so would it be in our best interest to grab 256 kilobytes from 5 million sources individually at the same time?
No.
Why?
Well, the client on your end that's got to put it all back together probably wouldn't be able to do it at the fast enough speed, so you could get pieces mixed up as well as you would have higher chance of data loss.
Okay.
That many sources.
Well, data loss is going to be protected through TCP/IP, which we'll talk about in here.
I don't know, you have to remember that apparently these people have hard drives made by God.
Mm-hmm. It's only 305 terabytes. It could be cloud space. All right, but in any case, there's multiple things on our local machine that hold us back from this. One is computation power, putting it back together, right? Another thing is read-write speed on your hard drive. That's probably the big one. So on your local machine, ultimately you're writing this 305 terabyte file to your hard drive. So in reality, we're writing the 1 or 2 gigabyte file to our hard drive. So we have plenty of space for that, but if you have multiple things coming in from the same source, well, from multiple sources rather, and we're having to write each of those pieces to file, and they're all coming in at the same exact time, now our read-write head is going to here, then 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 to here. So you start wearing down your hard drive. Okay, fine, solid state drive. Still as a resource, you got to share, right? You can only read and write so fast with a solid state drive. So now your slowdown point becomes your hard drive. Make sense? And you're bogging your machine down computationally because you're having to put too many things together at once. Okay, and you have to deal with the idea that you have, in our example here, 5 million individual connections opened up to the internet. Probably starts bogging your system down pretty quickly because every one of those connections is a socket connection. Well, how big is a socket connection? Well, let's just say even an individual socket is, I don't know, 100K? 100 kilobytes of code?
Where did you get this computer?
Yeah, I think that's fair enough. So we have 100K times 5 million. So that is what? So that's K. So times 1,024. No, I'm sorry, divided by 1,024. That's megabytes divided by 1,024. That's gigabytes. So how many of you have a machine with 476? Well, we need 477, I guess. 477 gigabytes of free RAM. We don't have enough memory to store all those sockets.
Jackson has the closest.
Yeah, what does he have? 32 or 64? 32. Okay. We don't have machines with that kind of RAM. So we physically can't open that many connections. Okay. Even if we look at a normal size file. So let's say we're downloading a 2.5 gigabyte file. So 2.5 times 1,024 is megabytes, times 1,024 is kilobytes, divided by 256. So that's 10,240 sources. So if we were going to simultaneously download from each piece of that at the exact same time and get 256 pieces at once. Okay, well, first of all, that means we can handle 2.5 gigabytes per second of data coming into our machine through our internet connection, which we can't, right? So first of all, you have that problem. Like I can try to open up 10,240 simultaneous connections, but I'm only hurting myself because my internet connection can't split that many ways. Does that make sense? You know, and on top of that, you're taking up what? 10,240 times 100 divided by 1,024 divided by 1,024. So you're taking up, actually, hold on, that was times 100 was 2. That was kilobytes, right? 2.5 gigabytes, megabytes, kilobytes. That's the number of kilobytes. So we're going to divide that by 256. That's the number of 100 kilobyte chunks, 10,240. So,
You got an extra 0. 10,
no,
40.
this is right. So that's the number of 256 kilobyte chunks, correct? So each one of those then, so if we divided that by, actually, hold on.
No, each one of those is 100. And then each one of those chunks is 100 kilobyte for the connection.
This is the original file size, 2.5 gigabytes, times 1,024 gets us megabytes, times 1,024 gets us kilobytes, divided by 256 gets us our chunk size for Bit-torrent. So that gives us 10,240 pieces that we're dealing with. Okay, so 10,240 total pieces, each of which is 256 kilobytes. All right, so 10,240 pieces And so let's divide that. Actually, let's go this route. Let's say I can get on my internet. So I have 50 megabit per second. So 50 divided by 8, actually 100. I have 100 divided by 8. So I have 12.5 megabytes per second. So that's 12.5 divided by 10 to 40. Okay, so that means if I divide my bandwidth up by that much, I can get 0.001 megabytes per second from each source. So times 1024, so it's 1.25 kilobytes a second. Well, it's not so hot. So if I want to divide up this file, this 2.5 gigabyte file, I want to download it simultaneously from 10,240 sources, I'm only going to be able to pull 1.25 kilobytes per second from any single source. Right? And at the cost of how much memory? 10,240 times?
So that you 126 kilobytes per.
That's
source.
100K. So that's per socket. So divided by 1024, that's 1,000 megabytes. Divided by 1024, so almost a gigabyte of your RAM in your computer. So a little less than a gig of your RAM. So a lot of us have 8 gigabytes of RAM. So we're going to take up 1/8 of our total storage space in our computer for random access memory to open up 10,240 simultaneous socket connections, which then bogs down our internet completely, right? Because our download is only as fast as somebody else's upload. So chances are all those 10,240 sources can provide us the file at 256K a second, right? Upload seems reasonable, right? Because even the slower internet.
You said you can get.
Well, I mean, at that point, isn't the limit not their upload but your download?
Correct.
Because you can only download it at
what's a slower upload speed? 384 maybe? Kilobits per second? If you have like a slower internet, you might have 3 megabit down by 384 up.
I don't know, what do you have on this?
I don't know the upload speed.
They have a little puppy.
Yeah.
You tie a little note around his neck.
It's by carrier pigeon.
You just attach like a USB drive to it?
Maybe it's 768. I think 768 kilobits
paper
might be what the smallest I've
I
seen.
think that's what it is.
Little paper
Okay.
Sure.
So that's 96 bytes.
Exactly.
So that's 96 kilobytes per second. So our slowest upload speed will actually be 96 kilobytes per second from anybody's internet connection. So actually, you'd probably be able to download a little quicker because you'd have a bog down on this side because you're trying to get 256 kilobytes from them. And so 256 divided by 96. So it's going to take you 2 2/3 seconds to get a file from each of those individual pieces at their maximum download speed or maximum upload speed. You can only maximally download at 1.5 kilobytes per second, right? Well, they can give it to you at 96 kilobytes per second. But you can only maximally download it from them at 1.5 kilobytes per second. So 256 divided by 1.5 is 170 seconds. 171 seconds divided by 60. So you're at just under 3 minutes.
Sure.
So at maximum speed from 10,240 hosts in 2.84 minutes, you can get a 2.5 gigabyte file if you have 100 megabit per second internet.
Desolation of smog in HD.
That's not horrible.
3 minutes.
And you only had to use 1 gigabyte of your system memory.
Yeah, seems reasonable.
Okay.
And you can get it from all people that have, backcountry internet.
Yeah. So, but now let's do an experiment. That's if we open up 10,240 simultaneous connections. Okay. What if we only opened up 1,000 simultaneous connections? Okay. So 1,000 simultaneous connections. So we're going to take our 2.5 gigabytes. Let's just do divided by 1,000. So we're going to get 0.0025 gigabytes from each of those sources. So times 1,024, that's megabytes. 2.56 megabytes from each of those sources. Okay? So now we have, actually, let's just go back down to 1,000. No, we do multiply by 1,024. So we're going to get 2,621.44 kilobytes from each of those sources. Divided by 256 is 10.24 chunks. 10.24 256 kilobyte chunks. Now we're going to multiply that so we have that divided by 96. So that means we're going to have 27 maximum chunks at 96 kilobytes a second. So right? That divided by 256, that's the total number of chunks is 10 for each of those parts. But they can only serve it to us at 96K a second if they're all slow. So that means we're going to have to go in for 27.3 96 kilobyte chunks. All right. So somebody remember 27.3. Just copy that real quick. All right. So now we're going to say if I have 100 megabit internet, which is 12.5 megabyte internet, and I'm going to divide that by 1,000 sources, I can get 0.01 megabytes per source. Right? That's my split, is 0.01 megabytes per source. So divide that, or no, multiply that by 1,024. That's 12.8 kilobytes per second per source. So I'm still not getting it at their 96 kilobytes. They can give it to me. All right, so 12.8, 96 divided by 12.8 gets me 0.75. Hold on, 12.8. Gets me 7.5. So it's going to take me 7.5 seconds to get each of those 97 times, what was the number, 27.3? 27.3. So it'll take me 204 seconds divided by 60. So 3 minutes and 41 seconds to get that file from 1,000 sources. Not that much longer, right? Do you suspect that if we kept playing with the numbers, we might find a sweet spot somewhere in the middle? That's kind of the right balance between our download speeds, our memory, and time to actually get the file.
It's going to take far less.
You also are keeping in mind that all 1,000 of these people have to stay alive for 3 minutes and 41 seconds straight in order for you to really maximize your internet connection.
Hope it isn't Call of Duty.
Okay, so chances are for Bit-torrent, would you rely on there being, well, first of all, there's rarely 1,000 seeds, right? Okay, but if there was, would you count on 1,000 individual people on a single file being alive for 3.5 minutes? No, it would never happen, right? So that's going to have all sorts of performance issues as well. So there's some sort of delicate balance between how many peers do you connect to start downloading the file, and how much do you commit to any single peer. So that's why the packet size is, well, that's why the download piece size is 256K. They figure even in a slow internet situation, 256 divided by 96 is only 2.67, 2 2/3 seconds of time. So they're only relying on a single seed being alive for under 3 seconds for a single piece. And that seems significantly more plausible, right? You just think about the amount of time when you finish downloading a torrent and when you actually get to your machine, because you finished watching your Netflix show or something like that, and you get to your machine and say, oh, it's done, now let's remove it. So in that period of time, how many 2.6 second periods were there? And that's the number of chunks that you were able to share with the world. Kind of make sense? And that's only one source. Now, when you're using Bit-torrent, often you're seeing your upload speed is one number, your download speed's another. And typically your download speed's a lot higher than your upload speed, right? Okay. Now, there usually is some sort of balance where they're only going to let you download at a certain speed depending on what you're willing to do as your upload. But for popular torrents, everything just goes through the roof because there's, 400 seeds or something. But in any case, we're only relying on a single seed to be alive for 2.6 seconds at the slowest download speed. Now, if we take our average download speed, so let's say that most people have an upload of what, 1.5 megabit? Is that our average? Probably. So that's 96 times 2, so really it's just half that. So 2.66 divided by 2, so 1.3 seconds. That seems even more plausible, right? Okay. Now, what other time wasters are in there? So if we have back to our picture here, and let's just say these guys these are the 3 people playing ball here. So this guy just grabbed a 256K chunk from this guy. This guy grabbed a 256K chunk from this guy. This guy grabbed a 256K chunk from this guy. It's just going around, and then as new seeds are joining,
Trace rate, amount of time it's going to take for the files to get across. Data loss during the transfer and after you go back.
Okay. Well, so it's not so much once the files are on the network, then that's just propagation delay on the network. But while that's happening, we're still opening up another connection, so those overlap. But how long do you think it takes to establish a connection between this machine and this machine?
It would vary on how many connections are open to the machine.
But measurable time, right?
Yeah.
So let's say it's 100 milliseconds. So 100 milliseconds it takes to establish a connection between this guy and this guy. So then we download the file. That's after we open the socket connection, and then we close the connection. Now you might say, okay, maybe we leave that connection open until this guy drops off. But let's just use the example that we actually kill the connection. So I just finished grabbing an entire 256 kilobyte chunk. I kill the connection off. Well, now every single time I reconnect, it's going to be 100 milliseconds, 100 milliseconds, 100 milliseconds. So in our example, every 2 seconds, we're going to waste an extra 100 milliseconds to get a connection reestablished. So all these things start adding up to time. Does that make sense? All right, so now if we're implementing this, we have our server, we share the location of our server, so everybody's going to come in and download our torrent, and our torrent is going to give us the current setup of the network, right? So these guys get it. So they both downloaded this file. They open up the torrent, and now they start looking for data. Where do they look? Where do they look for the data? Do they go back to the main source? How does this guy know about this guy? They both know about the guy in the middle because they both just downloaded the torrent from him, and he just happens to be one of the peers. So this becomes an argument of how do peer-to-peer networks work? And this is really an example of a distributed peer-to-peer network. How does this guy ever know about this guy?
There's a server keeping track of everyone that's connected to start the download, and lets every new connection know, hey, there's these people as well, and I guess lets all of them know that, hey, this new guy joined.
Okay, so this guy here, Mr. Torrent, he's going to have a list that's going to contain this guy and this guy, right? These are the guys who downloaded the torrents, and when they first double-click on it, first start looking for it, they're going to connect here and say, I need a peer to connect to. So they're going to come here and request peers. And he's going to hand off peers that are hopefully less busy right now. Does that make sense? All right, so this guy at this point has a list of 2 peers. So this guy's going to connect to him. This guy's going to connect to him. So, but they both found out about each other through this middleman that was the public facing server, which was hosted inside the blah.torrent file. This told us where to go and find the list of peers. Okay? So he goes there, he gets his, he asks, I need a peer. So again, this is small data going back and forth as opposed to a big 5 gigabyte file. So he's going to say, I need a peer. So this guy's going to start collecting a list of peers. So once he collects a list of peers and this guy's in that list, he starts downloading one of the 256 kilobyte chunks from this guy. How does he know who has what files? If this guy is looking for the 700th piece of data from the 5 gigabyte file, how does he know that this guy has that?
The server didn't need to know. The server, you mean?
Well, this guy. This guy says, I need piece number 700. So he goes to the server and says, I'm looking for a peer who has access to piece number 700, because that's what I need to download.
Server, what, every time
How does this server know whether this guy has it?
every time that guy connects back to the server, it re-updates the tracker?
Okay, so when this guy connects to the server, because he's seeding the information, right? So, well, most of our machines, most of our torrents are seeding and downloading at the same time for a good period of time, right? Initially, what are you doing? You're downloading until you have enough to seed. Then you're doing both. You're seeding and downloading at the same time. So as you're downloading, when you go to open up that next connection to another peer, you're updating the server with the percentage of the file you currently have. So it knows how many pieces of that file you have. So this guy, the server, has this big Rolodex of all the peers and what percent of the file they have. Not just what percent, but specifically which parts of the file they have, right? Because chances are, because of the nature of Bit-torrent, these guys are not building their files sequentially. So this guy might have piece 1, 2, 7, 321, and 800. That's what he might have right now, just based on when he requested to get a piece, what was available in terms of what he needed, and what was currently available based on how busy they currently were. So load balancing. For instance, if this guy was the only guy that had piece 700, and this guy needed a whole bunch of pieces, and a bunch of people are already grabbing piece 700, it would probably be in this guy's best interest to not work on 700 right now, but work on a bunch of other pieces that aren't as busy, right? So this guy's going to say, I need a peer, here's what I need. This is what I currently have available that I'm looking for. And it's going to hand out a peer to this guy based on that. So you'll get an IP address, and then you can connect to that IP address. But wait a minute, we have a problem. So we go back to here. Oh, actually, we'll just copy this guy. Okay, so here's another guy. But now this guy, no, that would have worked. This guy's sitting behind a firewall right here. So this guy has a non-routable IP address, or maybe even a routable IP address, but the point is that you can't get to him directly. Well, this guy just contacted the server. The server says, oh, the guy that has the piece that you're looking for that makes the most sense for you is this guy. How does this guy connect to this guy? So now we're back to that same problem we talked about last time. This guy cannot rely on being able to directly connect to this guy. In fact, would you say that it's for the users of Bit-torrent, is it probably mostly common for the people who are using Bit-torrent to be sitting behind a firewall of some kind? Yeah, I mean, high 90 percentile of the people on the Bit-torrent network are going to be sitting behind a firewall because they're on their DSL, they're on their cable modem, they're on in a dorm, whatever it is. But they're sitting on a machine that may or may not have a real IP address, but more importantly, they're sitting behind a firewall. So whether they're reachable in theory or not, they're not reachable in practice directly. So this guy cannot open a direct connection to him. So this guy's going to now have to go back through the server. And this guy's going to have to go back through the server so that the server can now connect the dots between these two guys. Make sense how that works? So think about all the things that this server has to do. Let's back to this list. This list right here. So he needs to accept incoming connections. Okay, and incoming connections come in two flavors. Request 4 pieces and seeding of pieces. Seeding of, it sounds kind of creepy, but that's fine. Let's leave it. Seeding of pieces. Okay, so those are the two incoming connections. Okay, so I'm a torrent client, and I am interested in this particular file and this particular piece from that file, or really this collection of pieces from that file. Fulfill this the best you can. Okay, so now the server, his job is to do a bunch of calculations. Right, so understand what Bit-torrent has done in terms of the model. Bit-torrent has changed the client-server model from being a bunch of clients connecting to one server and sharing that one server's upload bandwidth. It's changed that to now they're all sharing that server's computation power. Make sense? And which do you think is more powerful? This server's computation power or this server's upload bandwidth? Computation power by a lot, right? Even if it's on a fast, a fast server, let's say it could upload at, let's say 1 gigabyte a second. Pretty fast. That would be a fast machine, right? 1 gigabyte per second. Well, 1 gigabyte per second, how many people would it take to maximize their connection? Well, if you have 100 megabits per second, that's 12.5 or 0.01 gigabytes per second. So you can handle 82 users simultaneously with that that upload bandwidth. That's if all of those users had that maximum speed, and you could upload at 1 gigabyte a second. How many places on the internet right now do you think can upload at 1 gigabyte per second? Maybe Google. Okay. What's a realistic high upload speed? When you download from someplace. Whenever you're downloading from a server, you're probably getting some subset of what your maximum download speed is, right? What would you say is the average speed you download from a server?
Wow, I've seen 12, 13 megs.
Okay. Well, is that common? Well, that's actually using your torrent. That's not from a single server.
Probably a couple of megabytes.
A couple megabytes a second?
It's like a good server.
Yeah, I would say that's fair. So now you have this one server sharing 2 megabytes of upload speed. Well, the 2 megabytes of upload speed, 2 divided by 12.5, if you have a 100 megabit per bit per second connection, you can't even serve one user. You can't maximize one user's internet connection. Okay, so even our fast servers, our fast internet upload speeds, pale in comparison to, a typical web server. We consider that to be a pretty robust computer, right? Well, what kind of computation power do you think that computer has? If you were to somehow, in some weird magical place, convert computation power to megabytes per second upload speed, thousands and thousands, maybe millions, a lot faster. Okay, so what Bit-torrent has done is it has shifted the use of this one central server from being a shared bandwidth resource to being a shared computational power source bandwidth or resource. Make sense? This guy can handle a whole bunch of tiny little downloads, and we're actually putting the burden on this guy for both of these. We're giving a little bit of bandwidth here and then the serving here, but realistically, most torrents, you're going to host the torrent file on some web server somewhere, and then the server you're actually connecting to is a different place. So you're not even sharing it between those two. But even in this example, this server is splitting its computation power among all of these guys. Okay, so what does that server need to do? It accepts incoming connections, which are going to be requests for pieces and seeding of pieces. It's going to keep track of current peers in terms of what they want and what they have. Okay, so it's going to keep either a database or some sort of data structure of these things for all the peers. Every peer is going to have a list of the parts, the pieces that they want, and the pieces that they have. And that's going to be the data structure that gets searched to hand out the right pieces to all the places, right? Okay, what else does it do? It connects sockets together. That makes sense? So what we're going to start doing next time is we're going to start building a little prototype program that connects sockets together. And we're going to build a little tiny data structure that kind of sort of solves this problem. And we're going to see how the Bit-torrent network actually works programmatically. What we're mostly interested in is, besides the high-level version of this, is how do bits travel over the internet in chunks? Okay, so how can we have this single server send, we're going to actually see how can we take a file from one machine and send it to a file on another machine. Building up files, because files are kind of a collection of bits. So thinking of you're receiving Legos and piecing everything together. Make sense? So we'll start looking at that next class. We may have a quiz involving this concept of Bit-torrent having taken away the sharing of bandwidth resources and replacing it with the sharing of computational resources. That's the important piece about what Bit-torrent does. We have lots of computational power, not so much bandwidth.